Hello everybody, and welcome to the beginning of section 4.4. We are looking at page 101 in the workbook, and the topic of this section is the fundamental theorem of calculus. That sounds pretty important, and it is, because it's going to unite the two major concepts of our course, the problem of finding a rate of change using the slope of the tangent line and finding area under a curve. I think the best way to illustrate that is with an example. So let's look at this preliminary example together. So in this particular case, we've got a small plane, starts at the end of the runway and accelerates towards takeoff. We're going to let S of t represent the position of the plane, and v of t represent the velocity of the plane. So notice that we have two different functions here, position and velocity. And what they'd like us to do is to write down two different expressions that represent the same thing, two expressions that represent the change in position of the plane between two time values of a and b. Okay, well, one way that we could represent that change in position is using the first of those two functions. Okay, if S of t really represents the position, we should be able to get that change in position by just subtracting two position values, S of b minus S of a. That would be a very direct way of measuring that position change. But there's another way that we could look at that, okay, by going back to something that we did in section 4.1. The velocity function also gives us a way to measure change in position. Back in section 4.1, you did a problem where you found the area under the velocity curve. I'm just going to shade that. Over here to the right, we've got a function that represents the velocity. And in that problem, you convinced yourself that the area under the velocity curve has distance units to it. It's measured in meters. And so we can measure that same change in position by taking the integral of the velocity function. Okay, so it turns out that these two things that we wrote down are equal. They represent the same number. They both represent the change in position of the plane. And so here's what we end up with. Very interesting equation that looks like this. The integral from a to b of the velocity equals S of b minus S of a. Okay, so let's think about this equation that we have in front of us here. So what is the relationship between the velocity function and the position function that we have in front of us? You might remember way back earlier in the course that velocity is the derivative of position. In other words, it's the rate of change of position. So what we've just discovered here is something called the total change theorem, okay, which you see in the box right below us here. And it says that if you integrate a rate of change, like this derivative function, what you get is the total change in your function. That's what's sitting over here on the right-hand side. Okay, and this equation that you see down here, the integral from a to b of f prime of x dx equals f of b minus f of a, that's the same equation as what we have up here with velocity and position. Okay, and what's interesting is we can state this theorem, this total change theorem, in a different way, and what we get is the fundamental theorem of calculus. So in the equation above here, we can see that f prime of x is the derivative of f of x, the function on the right-hand side, but we can turn that statement around and say that the function f of x over here is an antiderivative of f prime of x. Okay, antiderivative is a new word, but it's really just the reverse of a derivative. Okay, so if we change the language around, here's what the total change theorem sounds like. If little f is continuous and capital F is an antiderivative of little f, then we get the integral from a to b of little f of x dx is capital F of b minus capital F of a. Okay, so a couple of comments here. First thing, these two theorems, the total change theorem and the fundamental theorem of calculus, they really say exactly the same thing. They just use the language in a little bit different of a way. Okay, and secondly, the fundamental theorem of calculus is a very powerful tool because it gives us a way to find the exact value of an integral, provided that we can find an antiderivative of the function that we're integrating. Okay, and the rest of this section we will explore some examples that illustrate the use of the fundamental theorem of calculus.